Okay guys, so I'm going to do a quick little thing here with z-scores and sampling distributions. What I talked about in the previous video was about z-scores as being standardizations of the values of a single x variable, where all the values of x are here, right? And every value of x has a corresponding z-score. Well, remember we also then talked about sampling distributions, where a sampling distribution was normal, and the values along the x-axis weren't of x, but were of x bar, and of course we're assuming that our n is greater than 100. No need to think about that right now, but that this is a sampling distribution, right? Yeah. And it's a little bit different in that what we've got here are all the different x bars that could occur, or sample means that could occur, given different samples that we took, right? And we know that these sampling means pretty much go around the overall population mean, the true population mean, which of course is z is 0 here. So before we were saying we had problems where we said, what's the probability if I randomly pick an x? What's the probability if I randomly pick an x from x observation that it would be greater than whatever this x is? Okay, that's not what we're doing with sampling distributions. Now we're asking questions like, what's the probability that I would take a sample of a certain size, calculate the sample statistic, x bar or p, if we're using a binary variable, what's the probability that that sampling statistic would be greater than mu, less than mu at these different points? So let's say this is, let's say mu again is 120, and this is 100. And we know that, let's see, let me just go ahead and look at this example here. If the standard deviation was, the standard deviation was 20, then we know that the z here is -1. And if we looked up a z, the p-value for z at -1, that would tell us the probability of taking a sample and getting an x bar from that sample that is 100 or less. Okay, does that make sense? Okay, so let's do an example with this, except instead of using x as a binary variable, let's assume that it is a, instead of it continuous, let's assume it's binary. Okay, so here we go. Let's assume that we've got a normally distributed sampling distribution of proportions for a variable x that is binary. Okay, and it represents something, the proportion of, or x is binary, it's a 1, 0, so let's just gender in professional executives association, something like that. So 1 is male, 0 is female, 1 is male, blah 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 blah. Okay, we have a bunch of those, right, in our population, and we take a sample of the population and we will get a proportion, right? So this is the proportion of males in some professional organization, and let's say that we took a sample and got 0.30, and let's say our sample size was 500, and let's say also that it is known that the population proportion, or pi, is 0.40. Okay, so all of our proportions are across here. The mean proportion, or pi, is 0.40. Okay, we took a sample of 500 and we calculated a proportion of 0.30. So here we go, there's 0.30. So we know that there are a bunch of z's that correspond to these p's. right here, the z is 0. And we can go to our z table and find out what the p-value is here if we knew what the z was. So we have to find the z that corresponds to this p of 0.3. And that would tell us, what would it tell us? It would tell us what's the probability that if we took a sample, we would get a proportion of 0.3 or less, given that the distribution looks like this and the mean is 0.4. What's the probability that we take a sample and calculate the sample statistic, which is a x bar or a p, and get a sample statistics that is less than some number or greater than some number? So what's the z here? Well, we're going to use our little formula. Over the standard error. And we know, oh, standard error, I should be figuring that out somewhere else. Okay, so let's not do it there. Let's do it up here. Standard error is, let's use the square root of pi 1 minus pi, since we have pi 1 minus pi over n equals the square root of, what's pi? 0.4. We should have written that down over here because we want to write down everything we know in the same spot. So we got 0.4 times 0.6 over 500, and that will give us 0.22. That will give us the square root of 0.048, which is 0.22. Okay, so that's the standard error, and we're going to put it here, right? So let's do p 0.3 minus 0.4 over 0.22 will give us 0.10 over 0.22 will give us minus 0.45. Okay, so we'll go all the way back and we see this is what we've calculated our z. So the z at 0.3 is minus 0.45. Okay, we go to our z table and we figure out that the p-value at that point is 0.3264. Okay, so that's the p-value in here at 0.3 z of minus 0.45. And it tells us if we were to take a sample of 500, what's the probability that we would get a sample proportion of 0.3 or less? And the answer is 32.6% is the probability that that would happen. Okay? All right, so anyway, that's the difference when we're working with these z's scores for sampling distributions versus the first video, which was just for x variables. Okay. Trying to turn you off.